Hi there everyone, this is Navigating Intrinsic Triangulations by Nicholas Sharp, Yousuf Soliman, and Keenan. It was originally presented at SIGGRAPH 2019. Who knows what's wrong with this mesh? Really, nothing's wrong with it. It's a perfect description of the underlying shape, and it's even manifold. But many geometry processing algorithms from SIGGRAPH and elsewhere would struggle with this shape, because it has skinny triangles and an inconsistent sampling of vertices. You might try remeshing it, but even after 3 decades of research, there are still no foolproof solutions there. You risk either adding a massive number of new elements or degrading the underlying geometry of the shape. The heart of the problem is that we expect the triangulation to serve 2 distinct purposes. First, the triangulation encodes the geometric shape of the object. And second, the triangulation serves as a data structure to support computation. Triangulations that are well suited for one of these roles are often ill-suited for the other. That's why traditional remeshing will always be hard. It's searching for one triangulation that serves these 2 often opposing goals. I'm excited to share our work on intrinsic triangulations, which escape this dilemma by allowing the triangulation that supports computation to differ from the triangulation that encodes shape. The basic notion of intrinsic triangulations has a long history in mathematics, but to really put them to work in geometry processing, we've developed a new signpost data structure, which makes it easy to create, update, and make use of these intrinsic triangulations. We also explore algorithms for constructing intrinsic triangulations. In particular, for the first time, we perform intrinsic Delaunay refinement of surfaces, and it turns out to be extremely effective. Equipped with these tools, we demonstrate how our intrinsic triangulations allow robust realizations of classical algorithms from geometry processing. The key here is that we won't have to reinvent all these existing algorithms. They'll automatically inherit some pretty fantastic robustness properties from our data structure. Ultimately, we'll be able to produce quality triangulations, which exactly preserve the underlying geometry, can be efficiently constructed, and fit nicely with existing algorithms. We see this as a major step towards a much-needed future of black box geometry processing. Think about how we use linear solvers. You probably don't know the details of the data structures used by a sparse solver under the hood, but it'll do what's necessary to efficiently output a numerically trustworthy solution. This is as easy as typing / in MATLAB. Geometry processing should work the same way. Alternate representations like intrinsic triangulations can be used under the hood, automatically generating trustworthy solutions to numerically difficult problems, rather than putting this burden on every single top-level algorithm designer. How would this black box actually work? Well, suppose you have some input where computing directly in the input mesh wouldn't work well. Instead, you can build a corresponding intrinsic triangulation, run your computation there, and then transfer the result back. This offers robustness to surface geometry programs without any conceptual changes to existing algorithms. To put this in context, there have been many excellent papers about robust geometric algorithms at SIGGRAPH and elsewhere. Each of these offers a robust algorithm for a particular problem. But instead of tackling a single problem, our work here builds a bridge which immediately improves robustness for a broad class of existing algorithms. A few other methods have also built such bridges, but ours is the first which handles surface geometry and immediately plays nice with existing algorithms. So just what are these intrinsic triangulations? Well, let's remember what makes a triangle. A Euclidean triangle is one that has straight edges and a flat interior. And as we all know, once you know the 3 edge lengths of a triangle, its shape is totally defined. Any other quantities like its area, its angle, its cotangent weights, and so forth can easily be computed directly from these edge lengths. So let's run with this definition. I'm going to argue that this triangle here meets our definition. It may look bent, but its edges are geodesic paths across the surface, which basically means they're straight. And there are no vertices on the interior of the triangle, which means it has a flat interior. It may seem bent, but we can lay it out in the plane by these 3 edge lengths, and other quantities like areas, angles, and so forth can easily be computed and do not change from the bent configuration. That tells us that this bent triangle is really a perfectly good Euclidean triangle. And because everything's Euclidean, you can use good old-fashioned linear elements and piecewise linear interpolation on this kind of triangle. Of course, you can keep going and triangulate a whole shape. You're probably used to seeing triangulations of the cube like the one I've shown on top. But there are other, more interesting intrinsic triangulations of a cube, which encode the exact same shape, but make use of these bent triangles. So then the question is, algorithmically, how do you represent these interesting intrinsic triangulations? Well, there have really only been two previous approaches. A first idea is to store only the mesh connectivity and edge lengths of the intrinsic triangulation. This is elegant and easy to work with, but unfortunately important information has been lost. You no longer know the relationship to the underlying surface. A second idea is to explicitly store every location where the underlying mesh and the intrinsic triangulation intersect. This is informative, but it's cumbersome and expensive to work with. We've come up with a new signpost data structure, which gets the best of both worlds. It's abstract and easy to work with, like the lengths, but it's also a complete representation, which will allow us to do pretty much anything. As a bonus, it becomes very easy to represent problems involving tangent vectors. The core idea of our data structure is very simple. We store not just the length of every intrinsic edge, but we augment this with the direction of every intrinsic edge from each endpoint. We call this data signposts, because for each edge, it tells you the direction and distance to walk in order to trace out an intrinsic edge across the surface. In particular, we store these angles in tangent space with respect to a fixed, arbitrary reference direction at each vertex. To be really concrete about the data we store in our signpost intrinsic triangulations, we keep track of the connectivity of the intrinsic mesh, the location of each intrinsic vertex as a point on the original surface, the length of each intrinsic edge, and the direction of each intrinsic edge from each of its endpoints. This representation is implicit. Its complexity depends only on the number of intrinsic triangles, not on how the intrinsic triangulation overlaps the input mesh. This implicit representation can be made explicit by tracing out these edges along the surface, which we do lazily only when needed. This tracing is a cheap and easy operation. It just amounts to a whole bunch of 2D line-line intersections. A big part of our contribution is to describe algorithms for many standard mesh operations on these intrinsic triangulations. Across the board, the implicit representation makes it easy to implement these operations, and efficient too. Let's walk through some mesh operations on intrinsic triangulations using our signpost data structure. The most basic operation is an intrinsic edge flip, where you take one edge of an intrinsic triangulation and flip it, like you see on the right here. To be really clear, I don't mean an extrinsic edge flip, which would degrade the geometry of the shape. I mean an intrinsic edge flip, which preserves the geometry but creates a bent edge. To evaluate an intrinsic edge flip in our signpost data structure, we'll first take the edge to be flipped and lay out both of its adjacent triangles in the plane from their edge lengths. We can then measure the length of the new edge which is going to be created, and we can measure the direction of this new edge from each of its endpoints by taking an offset from some neighboring direction, which we already know. Finally, we can update the connectivity of the intrinsic mesh. The same procedure applies even if we're deep in some complicated intrinsic triangulation, which has some crazy overlap with the original shape. And it's always a constant time operation, no matter how complicated the intrinsic triangulation is. We can also insert new vertices into our triangulation. This was prohibitively complex to do with previous data structures. Given barycentric coordinates for a new vertex in some intrinsic face, we can first lay out that face from its three edge lengths, just as before, and place the new vertex in this layout. We can then measure the lengths of all the new edges we need to create and compute their direction, again by computing an offset from some known neighboring direction. One tricky detail is that we need to find the location of this new vertex on the original surface. Just knowing its barycentric coordinates in an intrinsic triangle doesn't immediately tell us its location on the original surface. But we can get that by just tracing out one of the edges whose length and direction we just determined. Wherever that tracing ends is the location of this new vertex on the original surface. And finally, we again update the connectivity of the intrinsic mesh. Notice that this procedure preserved all of the invariants of our signpost data structure. Each triangle is a flat Euclidean triangle with geodesic edges and no curvature on its interior. I won't go through all of these in detail, but we can do pretty much all of the standard mesh operations you would expect, as well as evaluating correspondence between points on the input surface and points on the intrinsic mesh. One thing to notice is that one operation we never do is we never remove the original vertices of the input shape. That's because those original vertices have a curvature at them, and we need to maintain the invariant that all of our intrinsic triangles have no curvature on their interior. Now that we have a simple and effective data structure for representing intrinsic triangulations, we can start building interesting and useful triangulations. The consistent theme here will be that algorithms from the plane already work extremely well on surfaces under our framework. Before we get too deep, a quick key about how to read our figures of intrinsic triangulations. The black wireframe edges denote the original input mesh, and the bright colored triangles are the faces of the intrinsic triangulation that we're working with. Of course, the mesh operations we just outlined are extremely general and open the door to a wide range of possible remeshing algorithms. It just so happens that many of the best remeshing algorithms from the plane make use of the Delaunay property. We studied 3 different algorithms in this framework: intrinsic Delaunay triangulations, intrinsic Delaunay refinement, and optimal Delaunay triangulation. In all cases, we'll see that these methods generate meshes which have great computational properties, don't require adding too many elements, and do all of this while exactly preserving the geometry. Delaunay triangulations are a fundamental object in computational geometry. Among other things, they guarantee that the Laplace operator has all positive edge weights and a maximum principal. There are a lot of equivalent characterizations of Delaunay triangulations in the plane. The one that's useful for us will be that for every edge, the opposite triangle angles sum to less than pi. On an intrinsic triangulation, we can evaluate this definition by simply laying out the 2 triangles on either side of an edge and measuring those 2 angles in the plane. We'll say that a triangulation is Delaunay if all of its edges are Delaunay. There's a wonderfully straightforward algorithm for producing intrinsic Delaunay triangulations. While any edge is not Delaunay, flip it. And that's it. A surprising and beautiful result is that this simple procedure will always yield the unique intrinsic Delaunay triangulation. Here's an example of running this procedure on a CAD model. Notice that the intrinsic triangulation can be very different from the mesh that you started with, and might involve lots of complicated and interesting intrinsic triangles. On the theory side, the worst case performance of this algorithm is still an open question, but I can assure you that in practice, it's extremely fast and effective. We ran this intrinsic edge flipping procedure on each manifold mesh from the Thingy10K dataset. Here on this plot, the x-axis is the number of edges in each mesh, and the y-axis is the number of flips it took to make it intrinsic Delaunay. Notice that the trend is extremely linear, and there are no outliers where the number of flips required was more than a small factor of the number of edges. And this is even on CAD models, which are typically the hard inputs for these kinds of algorithms. Generally speaking, these Delaunay edge flips take less time than reading a mesh from disk. Our implicit signpost data structure is up to 30 times faster at this procedure than past explicit methods on difficult inputs. Also, our implicit structure is much easier to work with, which allows us to implement more advanced operations and algorithms which weren't possible with previous data structures, the most important of which is intrinsic Delaunay refinement. Although the intrinsic triangulation you get from edge flipping, which you see on the left, has some very useful properties, it could still have very skinny triangles or a poor sampling of vertices. Delaunay refinement addresses this by judiciously inserting new vertices into the triangulation. The mesh on the right is not just Delaunay, but also the smallest angle in the triangulation is 30 degrees, and it has a reasonable sampling of vertices. Once again, we find that the algorithm from the plane works pretty much out of the box on surfaces here. We use an intrinsic version of choose second algorithm, repeatedly flipping edges until the mesh is Delaunay, while also inserting vertices at the circumcenter of skinny triangles. In the plane, this algorithm is known to converge to triangulations with angles no skinnier than 30 degrees or so, and we observe essentially the same behavior on surfaces. One tricky detail that shows up on surfaces is how to find the circumcenter of an intrinsic triangle. In an acute triangulation, this is easy. The circumcenter is just some point inside the triangle. But for an obtuse triangle, the circumcenter might lie outside the triangle. Here, we construct a vector which points towards the circumcenter and trace out that vector along the surface. Wherever the tracing ends, we insert a new vertex at that location. Here's some examples of intrinsic Delaunay refinements. These are really win-win meshes. Not too many elements, good angle bounds, the geometry is exactly preserved, and the algorithm runs in a fraction of a second. This is really exciting to me because for the first time, triangulation of surfaces is starting to look like triangulation in 2D. There are no tolerances, no trade-offs, no relaxations, you just ask for a nice mesh and you immediately get one. We had to slightly generalize how we think about the problem in order to get there, but we really got something awesome in return. And you can actually use these intrinsic triangulations to implement all kinds of other triangulation algorithms beyond what I've already described. In the paper, we further explored optimal Delaunay triangulations and also generating Steiner trees by inserting new vertices to induce shorter minimum spanning trees. See the paper for more details. Now, let me convince you that these intrinsic triangulations are actually easy to make use of in practical algorithms. The intrinsic triangulation you're working with might sit atop the input geometry in complicated ways, but the implicit representation we expose is always simple and easy to use. It's just a mesh which has edge lengths and areas and all of this data you're used to using in your algorithms. The general pipeline will always be build a good intrinsic triangulation, run some existing algorithm on it, and then copy the result back. In the examples I'm about to show, that's all we did. We built an intrinsic triangulation using one of the schemes I described previously, like intrinsic Delaunay refinement. We naively ran some existing algorithm on that intrinsic triangulation, and then we copied the result back. As a warm-up, suppose you need to solve a Poisson problem on a mesh. You could run our intrinsic version of choose-second algorithm to get a good intrinsic Delaunay refinement. Then, build the Laplace operator for the intrinsic triangulation, and solve the linear system there. This turns out to be twice as accurate as the best extrinsic remeshing scheme we could come up with for the same budget of elements. For many applications, you can do even better by doing more work on the intrinsic triangulation. As a more interesting PDE-based problem, consider using the heat method to compute geodesic distance, which basically amounts to solving two PDEs. Running this procedure directly on this badly triangulated input mesh results in more or less total garbage, with 60% error from a ground truth solution. Just performing intrinsic edge flips and running the same algorithm already reduces error significantly, down to about 20%, but running our intrinsic Delaunay refinement works wonders, taking error down to just 0.7%. This process is simple, fast, and didn't even need to double the number of vertices. Our data structure also makes it easy to process tangent vectors. Here, we smoothly interpolate tangent vector data defined on the boundary into the interior of the shape. Doing this naively can result in flipped vectors, which point in the opposite direction you would expect, which I've highlighted here in red. This happens due to negative weights of the Laplace operator for the original mesh. Running this exact same procedure on our intrinsic triangulation will never ever yield these flipped vectors, and we can prove that via a maximum principle for the vector Laplace operator. Again, here's another vector field problem where we're simply looking for the smoothest vector field on a surface. Running the exact same field generation algorithm on a good intrinsic triangulation yields a vector field which is visibly much smoother and quantitatively has much lower Dirichlet energy. We can push this even farther and do adaptive mesh refinement of surfaces. This is a technique widely used in scientific computing to great effect, but which hasn't seen much use on curved surfaces. The basic idea is to refine a mesh only where a solution is interesting. Here, this process nicely resolves a harmonic Green's function about a point. We can use AMR to resolve parameterization problems too. Here, naively using a harmonic embedding yields a non-injective result. Simply performing Delaunay edge flips ensures the parameterization is injective everywhere by giving the Laplacian a maximum principle. And further running AMR with refinement resolves the solution well everywhere. Looking forward, there's a lot still to do with intrinsic triangulations. There's a big need for work on the computational geometry of these intrinsic triangulations. Do algorithms retain their same guarantees as in the plane? Similarly, planar geometry has escaped even the pitfalls of floating point via the use of exact predicates, and we'd love to do the same with surface triangulations to push robustness even further. One operation we didn't explore is intrinsic simplification, and that could probably be very useful in the context of surfaces. And since we're doing surface processing, here we work solely with manifold meshes, but it seems feasible to extend many of these techniques to the non-manifold case. I only scratched the surface here of potential uses for these intrinsic triangulations. This paradigm makes perfect sense for classes of algorithms like spectral methods, where all you really need to do is nicely resolve a spectrum of some operator. For surface learning, where you want invariance to an input triangulation. For compression, where the ability to change the connectivity of a surface without changing its geometry is very useful, and so many more problems. We've provided a nice code base, which will allow you to check out some of these algorithms, and the important point here is that we expose an intrinsic triangulation in a way that works just like a normal mesh, so it's really easy to map your algorithms onto this data structure. As a closing thought, we're very optimistic about the future where robustness can simply be a subroutine in geometric algorithms. Rather than having to stress about numerical robustness for every single algorithm you write, A huge class of these methods can instantly become robust in general just by running on our intrinsic triangulations. So please give us a try and let us know what you think. And with that, I'll close and thank you for your time.